Alrighty. So in the last one, I showed you some animations, and then we walked through about 3 examples. We'll try to get through a couple more examples in this one, and I think we'll wait until the last video to summarize all of those area/volume formulas for all the different shapes of the cross sections. Let's go ahead and look at number 4. It's going to ask us for y is equal to 2x squared minus 2, and y is equal to 2x plus 2. So that is a linear that cuts across a parabola. And the cross sections are rectangles where the height is twice the width, okay? If there's ever going to be cross sections that are rectangles, they're either going to have to tell you or they're going to have to imply what the relationship is between the height and the width, because obviously the width is the length of that cross section across the region, across the base. And there's no way beyond being told that you should be able to discern what the height is, okay? So here we want to know, we know that the height is twice what the width is. So that's always good. Let's go ahead and look at the printout that I made of that particular region. I stretched it out just a little bit so we could actually see the region just a little bit better, so please do pay attention to the scaling on this particular one. We see obviously the fact that this is y is equal to 2x squared minus 2, and this is y is equal to 2x plus 2, right? That's the linear, that's the quadratic. We know, because for this whole worksheet we have cross sections that are perpendicular to the x-axis. Okay. So that, of course, is what we're calling S this whole time. Just S for side. I mean, I really had no other variable that I really wanted to deal with that. Now, we know that the area is equal to the base times the height, and the height is twice this width, okay? So for this particular rectangle, the area formula is 2s squared. Okay, so just think of, remember, in all of these you want to visualize a solid sort of coming up directly at the camera, okay? So here it is, and there's a rectangle coming up that is twice as tall as the width is right here, okay? And of course, it's going to be shorter over here because 2 times this length is going to be less because it's shorter. And of course over here it's going to be even shorter where you have the length, or you have the width across the region, which is even shorter than that. Which is why, of course, S is a variable expression, because it is variable. It varies, okay? So we happen to know that S is going to be 2x plus 2, which is the top, minus 2x squared minus 2, which is the bottom. We can go ahead and simplify that a little bit. We get negative 2x squared plus 2x plus 4. And if we want to go ahead and factor out a negative 2, I don't really see any reason why we should, but for those of you that, just have that factoring compulsion, there you go. Now, obviously, we're thinking about cross sections from this point of intersection to this point of intersection. It just sort of goes across, okay? This point of intersection is rather obvious. That is actually negative 1, okay? And if you're looking at either one of these, you need to remember that this is 2, and then it becomes x plus 1, x minus 1. And this, of course, is 2x plus 1. So when we have it at 2, it's going to be equal as well, because 2, if you plug in 2, this factor in the quadratic winds up being 1, okay, and you have the multiplicative identity property going on, and therefore 2 times x plus 1 and 2 times x plus 1 just gives you an output of 6, because it's 2 times 3. So you're running from negative 1 to positive 2. So let's go ahead and put those limits of integration. Negative 1 to positive 2. Now remember, I'm going to need to take this area formula and plop it down in here, but I want S in terms of x, and I'm probably going to use this version right here, and then I simply need to multiply that by the width of each of those cross sections, and each of those cross sections, of course, has an infinitesimal width of dx, okay? Let's go ahead and use our calculator to figure this one out as well. We don't, and like I said before, we don't. We could figure it out by hand. I don't really care to do that simply because it would just take too much time. If I were still teaching you in person, we would do a whole lot more of that. Square dx, and no, why did I graph that? And we press enter, and we get 64.8. And notice that that's not an approximation. That looks like that is an exact figure. So we'll leave it at 1 decimal place, and we'll just circle it, and then we'll move on. Okay. So far, in terms of what we've been given, we have done a problem of cross sections, which involves squares. We did one with semicircles. We did one with an isosceles right triangle. We did one with a rectangle where the relationship between height and width was specified. The next one is an equilateral triangle. Well, that's a little bit more difficult, but not insanely so. I mean, it's a geometric formula, so we ought to be able to figure out a way to represent the area of an equilateral triangle with respect to one of its sides. And that's the first thing, of course, that we're going to need to do. Okay, so let's go ahead and let's ignore this for right now. Actually, let's go ahead and do it on the back of here. Now, an equilateral triangle is also an equiangular triangle, which means that it has angles, and of course this is not to scale, has angles that are 60 degrees, 60 degrees, and 60 degrees. So if I drop an altitude, a perpendicular altitude right here, doesn't that make it a 30, 60, 90 right triangle? And if this right here is S, this is 1/2 S. This is S. And this right here is √3/2S. Right? Because remember what the relationship is between the sides of a 30, 60, 90 right triangle. The relationship between those sides is 2 to 1 to √3. And all I've done with those numbers is I've just divided by 2. If I divide all of them by 2, the relationship between them is still the same. So if I have, and I know that the area of a triangle is 1/2 base times height. So in this particular one, the base is S. The height is √3/2S. So the area of an equilateral triangle with respect to its base is √3/4S squared. You might want to remember that. So let's go back to our problem. We know that the area of an equilateral triangle, it's kind of awkward subscript, but whatever, just work with me, is √3/4 side squared. Now the √3/, you're going to do it with your calculator, and the √3/4 is just going to be popped out in front of the integral anyway. It doesn't really matter. Now remember, when we were looking at this for the equilateral triangles, I'm not sure whether you actually took notice of what these functions are. It's y is equal to 1/3 x cubed, y is equal to 3x, and I've specified an interval right here where x is greater than or equal to 0. So I'm dealing with the cross sections that run across here between a linear and a cubic. This is y is equal to 3x, and this right here is y is equal to 1/3 x cubed. Now obviously for the interval, the linear is going to be on top. Now let's go ahead and figure out where they intersect. Okay, let's go ahead and multiply through by 3. That's supposed to be cubed. X cubed, so 0 is equal to x cubed minus 9x, which of course factors into that. So I know this point of intersection right here is that x is equal to 3. Well, that tells me that my limits of integration are 0 to 3. I know that root 3 over 4 is best just pulled out in front because it is a constant. I simply need an expression in terms of x representing s squared, and then I just need to tack on my differential, which is the width, making that area into a volume and turning it into 3 dimensions. Now, my s is going to be top minus bottom. So 3x minus x cubed over 3 squared dx. And that should be the correct integral, which accumulates and finds the volume of equilateral triangles. Just try to imagine equilateral triangles sort of sticking up off the page towards the camera with this as the base. And this integral will get us that volume. Okay. Oh, So root 3 over 4 times the integral of 0 to 3, and it's going to be 3x minus, so let's go ahead and do a proper fraction. Squared and dx. And we get 8.017. So 8.017 is our area for that particular function. Okay. Now, our volume for that particular scenario, whatever. Okay, let's go ahead and move on to the next one. This is number 6. We're back to squares on number 6. For no other reason than just because that's just what I happened to choose while I was creating this particular worksheet. And we have root x, negative cube root of x, and x is equal to 1. Okay, that's kind of an interesting one. The functions were a little bit bizarre, which is, I think, probably in retrospect why I chose to have rather simple cross sections. This right here is y is equal to the square root of x. This right here is y is equal to the negative cube root of x. And of course, x is equal to 1 is there to designate the fact that it goes from the intersection at x is equal to 0, and this is where my limits of integration, where my interval terminates. Okay. Now, obviously, the area of the face of all of the cross section is side squared. It is indeed a square. Okay. S happens to be root x minus a negative cube root of x. I guess you could turn it into fractional exponents if you want, and especially if you're going to wind up doing this by hand instead of using your calculator, you're going to want it in terms of that, not only for the foiling, but also for the integration. Now, we know that it runs from 0 to 1. This is my s. I need my s to be squared in order to make it a square, and I need my width in order to turn this from a square into a square prism. This is an infinitely thin square prism that has a height, or basically a side measurement of x to the 1/2 plus x to the 1/3, and I'm going to square it and multiply it by dx, and then I'm going to accumulate it from 0 to 1. So the infinite number of cross sections across this particular interval from 0 to 1, all standing up as squares off of that sheet of paper. Now let's go ahead and use our calculator again to figure out what that particular integral is. 0 to 1, parenthesis, we have the square root of x plus, now the cube root is here under math. If you press the math button, which is just under your alpha button, you have the cube root right here at number 4. So that's cube root of x, right space, so you get out from underneath the radical. And boom. I guess that's a difficult one because it sat there and churned for a second. That's 2.191 would be your approximation to 3 decimal points. Let's go ahead and I'll go ahead and call the video quits right here. We'll move on from here to do a couple more examples, and then we'll summarize all of the formulas for the different types of cross sections in the third video. And then we'll likely move on to 6.5 from here. So stay tuned for that. If you have any questions, as always, please do email me. Bye.